welcome. This is the model 2 lecture 9 and it is on kinetics of gas solid reaction, iron oxide reduction part 1. Actually, this iron oxide reduction kinetics I will cover in 2 lectures. In first lecture basically I will talk about the model and different rate controlling mechanism, and in the second lecture we will talk about the mixed control system and we will also solve 2 problems. Okay. So, this is the first lecture, and what are the concept covered? It will be basically we will talk about the mechanism of iron oxide reduction and then kinetic state sinking core model and the kinetics of chemical control process and gas film control process, as well as that is the ash layer diffusion control process. All types of control we will basically discuss. So, now there are basically when if we want to make a predictive model for the iron oxide reduction, there are basically 2 types of models available. Basically, one is called the progressive reaction model, another is called the unreacted core model. What is the progressive reactive model? Progressive reactive model basically this is called the progressive reactive model. What you can find in this case, the solid material that is being reduced, okay, that are porous enough, that is porous, and the reductant gas or the reductant can easily penetrate through the solid material. Okay, as a result, what happens? The reaction can take place throughout the body because the material is porous and it is porous to the gas, reductant gas. So, it can penetrate anywhere into the body. So, your reaction will start from the beginning throughout the body. Okay. Although truly speaking, there is a reaction may not be totally uniform throughout the body because the surface reaction will be more because the reductant concentration is more at the surface, but eventually this gas will penetrate inside and the reaction will take place. So, if you can see, there is the concentration of the reductant, this is the concentration of the solid reductant, okay, and this is basically the radial position. You can see at the surface after some time, basically this is across the time, this time is increasing. So, after some time you can find there is a concentration of the solid reactant is minimum at the surface, this is, and there is little higher in the core because the core is reduced little less compared to the surface, but eventually throughout the body the reaction is taking place. Okay. So, after some time you can find this is like this. So, both, that is the core has reduced significantly as well as the surface also reduced, but the surface reduction little more than that of the core, but eventually the reduction is taking place. After some time you can find that the reduction almost going to near to complete both near the surface as well as the core. Okay. It is becoming flatter and finally it will be. So, this is called the progressive reaction model where the reaction is taking place throughout the body because the body is porous to the reductant gas. So, this is one model, okay. But this is not very actual situation, the real situation, because in most of the cases we will find in real situation after some time, if you just take the body and make a cross section, you will find at the center, at the core of the particle, there is some unreacted core. So, at the core of the body, there is an unreacted core because the gas cannot penetrate the core so easily. And most of the cases solid are very dense and the penetration of the gas, that is the gas penetration is not that easy. Okay. So, gas basically cannot penetrate the solid body. So, what happens? The gas react on the surface and the reaction interface move from the surface towards the core. So, basically progressively the reaction approach from the surface towards the core, and unlike progressive model, the reaction do not take place throughout the body. So, reaction always take place at the surface and then it progress towards the core, and this is basically, that is why it is also called the topochemical model. This is the name, it is the name from Latin word somewhere, that is the topo means for surface. So, surface chemical reaction, okay. So, that is the thing. So, you get the name topochemical model or the unreacted core model, where the core with time shrink, the core with time, unreacted core, not the unreacted core moves with time shrinks, that you can find here. So initially it was the unreacted, after some time you can find this is the unreacted core, and this is basically the reacted one, that is ash layer. It is also called the ash layer, and ash layer is usually the porous, and that allows the gas to pass through, okay, and the reaction always take place at this interface, and after some time you can find there is the unreacted core has sink further. This is the unreacted core, but eventually there exists an unreacted core, okay, and there is, this is called the ash layer. And so, but as we have seen pictorially, it is very sharp interface are very sharp. In a real situation that may not happen. There may be a diffuse interface. The interface may not be so sharp, unreacted core and the reacted one, that is not so sharp, it may be diffused enough. But for the sake of model, because if you want to give some handy correlation, analytical expression, then I have to have a regular object, and as a result regular shape, okay. So I would like to have a very sharp interface such that the model becomes, so this is, and after that you can find there is unreacted core has diminished, and finally it will be completely diminished, and this is the thing. So that is called unreacted core model or the shrinking core model, because the unreacted core is shrinking with time. That's why it is also called the shrinking core model. And shrinking core model, some assumptions are there, because if you want to write a model, if you want to give some handy correlation between the time and fraction extracted, that is the time, what is the fractional extraction or the fractional reaction versus time, if you want to make a correlation, then very simple analytical correlation if I want to make, then I have to make some assumption that makes the expression simpler. So first assumption in the shrinking core model, because they usually assume some regular shape, for the sake you consider a spherical particle, okay, a perfectly spherical particle. Okay. Second thing is that it considered that the solid is very dense, so it does not allow the gas to penetrate through it, that is, it becomes a shrinking core model or the topochemical model, that is the surface reaction. So the core shrinks, if it is, since it is the spherical particle, the core will shrink by in terms of concentric spheres, so it will decrease with time, okay. That is the that is, it will progress in terms of concentric spheres. Some spheres is with a reducing radius, right. And the sharp interface, as I said, the interface is likely to be diffused, that is, it cannot be sharp, because somewhere some porosity will be there where gas can penetrate, and it will be diffuse interface. What do we mean by that? So that is, suppose this is the unreacted core, and this is, and your ash layer, this interface will be somewhat like this, it may be very diffused. This is called a diffused interface, but sharp interface is this, where it is perfectly sphere, concentric sphere, okay. So that is the assumption. And it also assumes there is the fixed radius. Fixed radius means the radius does not change with time. Initially what was the radius, finally it is the same radius, only what happens is that unreacted core shrink, and over that you have a product layer is there, product ash layer is there, such that the total radius is constant. What I want to mean is this radius, this r, here it is what, and here also the same, this is also r, there is no change in this. So total radius remain constant, only thing is that unreacted core shrink with time and the ash layer grow with time, right, the total. So these are the assumptions. Based on this assumption we can develop the model. So kinetics of iron oxide reduction. Now let us see, when we understand that thing, that is the shrinking core model, what is that? In the same line, if we think that is the Fe2O3, a hematite spherical particle is being reduced, then what will be the situation after some time? The situation will be like this, because what will happen after your the gas penetrates, what will happen if you start with a, we have started with a hematite particle. So initially it was like this, it was completely hematite, and I am considering it is a dense hematite particle, and after some time, so after some initial reduction with the gaseous reductant, this will be the situation, this will be the layer structure will form. What will happen basically, when the reductant gas will reduce and a shell of iron will form, okay, a shell of iron will form, and at the interface there will be woostite, Fex, this is called the woostite, your This is the thing, the thin woostite layer. Woostite is usually called FeXO, better than you can write it as FeXO because non-stoichiometric compound it is not perfectly FeX. So FeXO. So this is the woostite layer. So you have an iron layer, iron product layer, and at the interface with the woostite layer, and you have two more layers. One is called the magnetite layer and the hematite layer. Now this thing, this is after some time it will form. Now how it is forming, that has to be seen. So it is one thing is the topochemical reaction, and then the reduction diffuse through the product layer. Then how the reaction progress, once it is formed, then after that reaction progress this way, your reductant gas permeated through this. This is a porous layer, ash layer. There is the iron layer, there is the product iron layer, that is also called the ash layer. It is quite porous. It allows the gas to diffuse through it. So after the iron layer has formed, then the gas basically will diffuse through this iron layer and come to the woostite iron interface and reduce the woostite. Okay? And how this magnetite and magnetite layer forms basically, this is basically you can consider in both the way. There is some, you can consider both the way. One thing is that you can think that is whatever the, that is the reaction that is taking place, that is the FeO plus CO at this interface, and then what it is telling how this will form, then this iron whatever is forming, that is the iron ion, Fe2 plus whatever is forming here, that can migrate from this layer to here, and it can react with this Fe, basically iron can react with your, these are the reaction that will take place. Fe3O4 at the interface, what is happening, your Fe3O4 can react with the iron and forming the FeO. So this reaction can take place and without any oxygen exchange. Basically you are just, iron will come and it can convert Fe3O4 to FeO. So if Fe2 plus is just permeate through this layer, and then here this reaction can take place. Just that Fe3O4 FeO interface, you can have this reaction, and this interface. So at this interface what will happen, this interface, so this is Fe2O3 and this iron has a diffused, there is the iron from here, it can diffuse in the form of iron ion, it can diffuse here, and after that it can react with the Fe2O3 and forming the Fe3O4. Okay. So this reaction can take place, or it may happen also, that is a reduction, because if they are permeable enough, that is if they are porous enough, that is the Fe3O4 layer is also porous, then in that case gas also pass through it, and can react at all interface simultaneously. That is also possible, but Fe ion also permeation or Fe ion diffusion is also possible, because when Fe2O3 is converted to Fe3O4, there is a crystal structure change, because Fe2O3 is HCP and Fe3O4 is FCC. There is a change in the crystal structures. Okay. So when it does, then there is a volume expansion. As a result, you have lot of defects are generated within this crystal structure, and because of this defects generation, there is the Fe ion diffusion also increases. So it is likely that Fe ion can diffuse from the iron layer at the Fe3O4 FeO interface, and this reaction can take place, and then this iron ion can also further permeate through the your magnetite layer and reach the Fe2O3 Fe3O4 interface, and then reduce Fe2O3 to Fe3O4. So it is possible. And also this reduction at all this interface, the reaction can also take place by gaseous reductant also. It is likely, because after the Fe2O3 is converted to Fe3O4, a lot of porosities are also generated that also help in permeation of the gas. So that's why such layer structure may also form by gaseous reaction at all interfaces simultaneously. So reaction not only gaseous reaction not only at this interface, but it can react in this interface. So what I am telling, all the interface, 3 interfaces are there. That is basically your, if I say this is basically one interface, that is the FeO Fe interface, then Fe3O4 Fe interface, then this is another interface, Fe2O3, Fe3O4 interface. So, at all this interface, gaseous reduction also can come and can reduce simultaneously all the interfaces, and it can form this type of layer structure. Okay. And then finally, this reduction of FeO to Fe will continue by the, what is that called, that is your that will continue by sinking core model, that is the unreacted core. This reaction will continue, there is the gas will diffuse and all interface it will react, and then all these unreacted core slowly sink like this. Okay. Or gas can only react at the FeO-Fe interface, and this layer can subsequently grow by the ion diffusion and reduction at the respective interfaces. Okay. Fine. So, these are the, let us see for sinking core model what are the kinetic steps that are involved. There are several kinetic steps that are involved here. You can see that is the gas. From this you can find there is a gas film also present there. It will also pose some resistance for the reactant. Suppose we are considering this reaction, that is a gas reacting with the B solid. Okay, B mole of B solid producing C mole of C solid and D mole of D gas, and in this case we are concerned with the B, reduction of B, okay, and by the reductant A gas. So, A is the reductant gas that is coming in. So, from here you can see this is basically the concentration profile. It is the concentration, CAG is the concentration at the interface, okay, at the film bulk interface. Okay. So, from here to here there is a resistance, there is the film resistance, because there will be some mass transfer resistance between these two interface. One is this exterior interface, right, this is the thing. So, you can find then there is a resistance in the gas film, there will be resistance. So, as a result you will have from here to here there will be a drop in concentration, because A concentration here and here concentration will drop because of gas film resistance, mass transfer resistance through the gas film. Okay. And there in the ash layer you will have an equal, then also A has to diffuse through the ash layer, there is also certain resistance, there is the ash layer diffusion resistance. So, from that's why there is also a gradient, and then the A reactant will reach the unreacted core surface, where basically the reaction will take place. And there is also a resistance, because chemical reaction resistance, because this concentration and final concentration is the equilibrium concentration. So, to attain that some resistance is there. So, think is that what are the steps? First, transport of the reactant A through the gas film, and then the diffusion of A through the ash layer, and then finally the chemical reaction at the unreacted core and the ash layer interface, and then your chemical reaction at the interface and the desorption of the product gas, that is the D that is forming, and then desorption, that is then transport of D through the ash layer, and then transport of D through the film layer, and then it will come out, right. So, these are the different kinetic steps are involved first, and either of these steps can control the process. Okay. If the transport of the reactant to the gas film is rate controlling step, because if the resistance is very high in the stagnant film, then that will be that can be rate controlling step when the resistance is maximum. And similarly, anyway, resistance is maximum is that is the thing, or if at the interface at the chemical reaction also can be the rate controlling step, and especially it happens when the temperature is low, then the chemical reaction is a very slow step, and that becomes a rate controlling step. And as we see, with the progress of time, the ash layer thickness also increases. So, after some time there is the diffusion through the ash layer also may be the rate controlling step. Okay. So, all possible things are possible, all possible rate controlling steps are possible. Thing is that which is the that you have to see, that is the which is the slowest step, or if the resistance of all the steps are comparable, then it can be a mixed control also. Okay. Fine. Let us first consider different rate controlling mechanism, right. So, first let us consider if chemical reaction as the rate controlling step, that is if the chemical reaction at the interface is the slowest step. In that case what happens, there will be no concentration you can find. In that case CAG is equal to CAS is equal to CAC, that is there is no concentration gradient at all, because these steps, that is the diffusion through the film layer, the transport through the film layer and the diffusion of A through the ash layer are comparatively much faster compared to the chemical reaction at the interface. As a result, you can consider this concentration are equal. Okay. Only you can find there is the drop in concentration, what is the surface concentration, and this is suppose the equilibrium concentration. So, you have to move from here to here, okay, equilibrium concentration. So, that is the that is the gradient. So, chemical reaction at the chemical reaction front there is a concentration gradient. What is the actual concentration to the equilibrium concentration? At the actual concentration at the core, that is called the CAC, to the equilibrium concentration, that is called the CAE, right. So, that thing. Now, how do you write the reaction for that thing? You just see. So, this is the reaction. Suppose a mole of A, that is the reaction I said, that is the B mole of B solid is reacting forming C mole of C solid and D mole of D gas. And then what is the rate equation? Rate equation you can simply write, that is from stoichiometry 1 by minus of 1 by B dNB dt, because B is getting consumed, is the solid that is getting reduced. Okay. So, minus of dNB is the number of moles of B, N is the number of moles of B, dNB dt, rate of change of moles of B with time, that should be negative because B is consumed, and A is also consumed, that is why minus of dNA dt. But you can find there is a because of stoichiometry is minus of 1 by B dNB dt is equal to minus of, because 1 mole of A is required to reduce B moles of capital B. So, you can write the kinetic equation like this, and this should be equal to now dNA dt, that is the rate of consumption of A at the reaction interface, that will be directly detected by a first order kinetics. That is the what will be the rate of consumption of A or consumption of B. So, rate of consumption of A at the interface will be defined by the first order kinetics. So, it is Ks is basically the chemical rate constant. Okay. Chemical rate constant, you can write it in centimeter per second, and this is the concentration difference, CAG minus CAE. Basically, CAG is equal to CAC. Basically, CAC minus CAE, you can write CAG minus CAE. And so, this is the first order kinetics into area. If you multiply it by the area, then it will be basically the moles per unit time, right. And then if you consider this the NB also you can write in this form, ND is the moles of B, since it is a spherical. So, 4/3 pi RC cube, IC is the radius of the unreacted core, okay. RC is the radius of the unreacted core, this much is the RC. So, this is the volume, that is the volume 4/3 pi RC cube into rho B is basically the moles of B remaining into the unreacted core at any time t. At any time t, this is the moles of B that is remaining in the unreacted core. So, dNB dt is basically if you just differentiate with respect to time, it will be 4 pi RC square rho B drc dt. And so, you replace dNB dt by this thing, and then you integrate from where, because initially the radius unreacted core radius was R, and then it has shrink, and at any time t it has become RC. So, it has changed, unreacted core initially was R, now it is RC, and initially it was the time was 0, now at time t it has become RC. So, if you now integrate this, so now if I integrate with respect to time, then what happens, let us see. So, if you find, then you will find this relation, that is t is equal to rho B, B Ks, CAG minus CAE, R minus RC. After that you will simply get that. And now see, you can calculate now total time for complete reaction. Time for complete reaction when RC becomes 0. So, if you put RC becomes 0, then the total time for completion tau is equal to rho B R by simple this thing, because RC is 0. So, now again if you can, now you can write the relationship in this form T by tau, because this is the inverse of tau. So, it is basically if you take this side, T by tau is equal to left out is what, that is 1 minus RC by R, and this is And xb, how you can write? You can see xb is basically what was the initial mass r cube, that is 4/3 pi r cube, all this thing, pi 4/3 pi r cube, 4/3 pi r cube minus rc cube by rho b. This is basically, initially this was the mass 4/3 pi r cube rho b, that was the initial mass, and in the remaining mass in the unreacted core is 4/3 pi rc cube rho b. So, this is basically, that is the mass that has been reacted. The mass that has reacted divided by the initial mass is 4/3 pi r cube rho b. So, it basically give you basically 1 minus rc by r cube. So, xp is equal to 1 minus rc. So, 1 minus rc by r, 1 minus rc by r basically 1 minus xb to the power 1/3. So, that is the relation that you get. So, T by tau. So, you got a relationship now, that is T by tau is equal to 1 minus rc by r is equal to this correlationship. So, if you plot, if you do some experiment in the laboratory, and then if you plot the reduced time versus 1 minus xb by 1/3, and it perfectly follows the straight line passing through the origin, then you can say that this is a chemical control process. Okay. So, similarly, let us see for, there is the transport through the gas film as the rate controlling step. If the all the resistance, maximum resistance lies in the transport of the gas through the film, transport of the reductant A through the film. Okay. So, in that case you can find, in that case what happens, you can say the major resistance, that is the major resistance lies here. So, all the concentration drops CAG to CAC only in this layer, right. So, in the film the complete concentration drops here, and beyond that there is no concentration drop, beyond that there is no concentration drop. Okay. This is basically the CAC is equal to CIE, because the chemical reaction is also fast. So, whatever the concentration at the unreacted core surface, that is equal to the equilibrium concentration, because your chemical reaction is quite fast. Only resistance lies in the film. Also the ash layer also there is no resistance, ash load resistance also very less in this case. So, there is no drop. So, CAG basically it directly comes in the film only, it becomes CAS, and CAS is equal to CAC, because there is no. So, all the concentration drop is here. So, this is the concentration distribution, and under that condition how you can develop the equation that you can see. So, again the reaction is this, and the rate equation you can write. Now, here dNA dt, that is the rate of consumption of A, is directly proportional to, that is called the, because it is the mass flux Kg into Ag at the heterogeneous interface. That is, here the mass transfer through the concentration boundary layer, mass transfer through a concentration boundary layer is basically defined in terms of mass transfer coefficient. Basically, it is directly proportional to the concentration difference across the CAG minus CAC or CAE. Okay, concentration difference, it is directly proportional to the concentration difference, and the surface area obviously depends on the external surface area 4 pi r square, and Kg is the proportionality constant. It is called the mass transfer coefficient. Okay. So, basically Kg into C is the mass flux through the concentration boundary layer. So, mass flux through the concentration boundary layer is defined in terms of mass transfer coefficient, where mass transfer coefficient is nothing, that is called the proportionality constant or the conductance, and it depends on the hydrodynamic condition of the gas film. Okay. Basically, there is the mass flux is directly proportional to the concentration difference across the film. Okay. And it is equal to a proportionality constant times the concentration difference, and proportionality constant is called the mass transfer coefficient, that physically means the conductance, mass conductance to the gas film. Okay, and it depends on the hydrodynamic condition of the gas film. If the film is very turbulent, or then mass transfer efficacy is very fast, then your Kg is also very high. If it is stagnant, then mass transfer coefficient is very small. Okay. So anyway, so this is the way it is there, and then mass transfer, basically this is the way you can calculate the mass transfer coefficient from dimensionless correlation. It is a very well known dimensionless correlation called the Range-Marshall correlation. This is called the Range-Marshall correlation. Range-Marshall correlation is basically for spherical particle, that is the, and then the spherical particle, that is the mass transfer across the film over a spherical particle. So, that is given by the Range-Marshall correlation. Here you can find the Sherwood number is dimensionless mass transfer coefficient. It is correlated with Reynolds number and the Smith number. Smith number is basically a ratio of mu by rho dm, basically diffusive, there is the diffusive momentum transfer to the diffusive what is that called, mass transfer. Okay. So, anyway, Smith number is basically a ratio of some mu by rho into dm, where dm is the diffusivity, mu is the viscosity, rho is the density. So, it depends on the physical property of the material. It is also a dimensionless number, Smith number, and Reynolds number, you know, it is also a dimensionless number, rho udp by mu. So, basically Sherwood number as a function of Reynolds number and Smith number are given, and this type of correlations are available. Several such correlations are available for different system, where you can get the mass transfer coefficient at any heterogeneous interface. Like here, it is the solid gas interface you have. Okay. So, similarly this type of correlations are available. So, you get it, but this is a very well known correlation for spherical system. Now, you can have this expression, and then you, if you integrate again, you can again dnb dt you can write in terms of drc dt, and then you can do this integration, finally you get this. And here also the time for complete reaction you can get, where tau is equal to, you can get from there, because RC becomes 0. So, it is like this only. So, tau is become like this. So, and again you can finally get the relationship between time and fractional reaction this way. Fractional reaction is T by tau is equal to 1 minus RC by R cube, that is XP. That simple T by tau is equal to XP, right. And you can find that tau is directly proportional to R, and chemical controlled also it was proportional to, that was, yeah, it is proportional to R. There is the diameter radius of the particle. There is a time for complete reaction is proportional to the radius of the particle, right. And T by tau relation is T by tau is equal to XP. If you do some experiment in the laboratory, and if you plot reduced time versus fraction extracted, fractional reaction, okay, and then if it follows the straight line passing through the origin, then also you can say that this is the gas film that is controlling the overall reaction, right. This is the reference, major reference of this lecture, Octave Levenspiel, The Chemical Reaction Engineering, John Williamson, Singapore, 1995. This is a very good proof on sinking core model. So, you can go through this book. And A.K. Biswas, there is a principle of blast furnace iron making that we have used here for, basically, that is it is nicely depicted in, that is the oxide reduction, layer wise oxide reduction, right. Okay. So, now come to the conclusion. In conclusion, what we have discussed so far is that, first thing is that iron detection can be visualized in a layer wise fashion by unreacted core model. That means the reduction of iron oxide can be nicely described by the sinking core model, and with an unreacted core of Fe2O3 at the center, and followed by a Fe3O4 layer, that is the magnetite layer, and then a thin oxide layer, and beyond which there is an ash iron layer, product iron layer. So, this is the way that is you can do that, and at any instant of time, that is the reactant gas will diffuse through the ash layer, first from the gas film and then the ash layer, and then it will react at the oxide interface, and it will convert the oxide to the iron, and oxygen will be entered into the gaseous phase and go away from the system. And subsequent layer formation can be done by the iron-ion diffusion through the magnetite layer, okay, through the oxide layer to the magnetite-oxide interface, and then it can reduce the Fe3O4 to FeO, that is the oxide, and then iron again can diffuse through the magnetite layer and reach the your magnetite hematite interface and reduce the hematite to magnetite, right? Or because in this case, as I said, there is the hematite reduction, hematite to magnetite reduction is accompanied with the volume change. As there is a lot of defects, as a lot of pores are formed into the structure, that can facilitate the iron movement, iron and movement. Besides, also we can think there is the gas also can diffuse through this product layer, like there is the iron layer as well as the magnetite layer, and can reaches the different interfaces. And at the all interfaces, gas can reduce. For example, at the hematite magnetite interface, it can reduce hematite to magnetite, and then magnetite woostite interface, it can reduce the magnetite to woostite, and the woostite iron interface, it can reduce woostite to iron. So by gaseous reduction also it can take place, or gaseous reduction can already take place at the woostite iron interface, and then that is the iron can diffuse towards the core, and then is subsequently reduced hematite to magnetite or magnetite to woostite. So whatever way you think about, but finally it remains a sinking core model. So and in the sinking core model, we have described here the two mechanisms of reduction. One is if it is chemically controlled at the interface, at the unreacted core interface. It is if it is the chemical controlled, then your reduced time to the fractional extraction correlation can be given by this. T by tau is equal to 1 minus RC by R, or 1 minus 1 minus x b to the power 1/3. Or if it is gas film controlled, that is at the exterior interface, is the gas film mass transfer through the gas film is the rate controlling step, then the relation is simply T by tau is equal to xp. And as I said, your in tau obviously depends on the mass transfer coefficient, and this mass transfer coefficient you can get from well established correlation available in literature in terms of Sherwood number. There is dimensionless mass transfer coefficient that is called the Sherwood number with Smith number and Reynolds number, and that is called the range Marshall correlations for the spherical particle. So for different system or different types of correlations are available, but for the spherical particle, mass transfer across the film is given by range Marshall correlation, very well known correlation. So you can use that to calculate the mass transfer coefficient and also calculate the total time for reduction if it is a gas film control. Okay. So this is the thing, and the next lecture basically I will discuss if the transport of A, that is the diffusion A through the product layer is the rate controlling step. So that we will discuss in the next lecture, as well as we will discuss if the system is mixed control, that is all the resistance in the gas film and the ash layer as well as at the unreacted core interface, chemical reaction at the unreacted core interface, if all are equally important, that means all resistance are comparable, then it can be better defined by a mixed control model. That we will also discussed in the next lecture, and next lecture also we will discuss two problems. Okay, thank you very much.